All right, I think we're going to get started. Our next speaker is Mike Krieger, who's a co-founder of Instagram and head of engineering. And without much further ado, Mike, it's all yours.
Cool. Thanks, Venkat. You guys hear me okay? Awesome. So today I'm going to be talking about how we've scaled the data storage at Instagram with a very small team, kind of an abnormally small one, I would say, for a company that grew as quickly as we did in terms of user base and data. So, hello. You may know Instagram. You hopefully know Instagram. We're a way of capturing and sharing the world's moments on your mobile devices. We launched on iOS originally in 2010, Android in 2012, and since then we've been kind of on a crazy rocket ship and just gone through a lot of rapid scaling. And at any point, if you zoom into the graph, it looks exponential, and you zoom out, you're like, oh, that's actually linear if you compare it to how things have gone. So we've been fortunate and also crazy over the last couple of years. So we hit 30 million users with basically 2 engineers who are focusing on any kind of infrastructure stuff. We hit 150 million with 6 engineers, I think like 4 of whom are sitting in this room, which is pretty great. So it's been kind of a rocket ship. We're obviously standing on the shoulder of a lot of open source technology with thousands and thousands of other engineers, but at least the core Instagram folks, until recently, we've only been about 6 people working on infrastructure. So what I hope you guys get out of today is really an understanding of our approach to solving these data scaling problems, more so than like, oh, this is exactly how they did it, because everybody's challenges are pretty individualized. So I think it's more about understanding how we think about these problems. And it has to boil down to one single thing. It's do the simplest thing first. So we will, this will be kind of a mantra throughout this presentation, but it's how we were able to scale with this small of a team. So what I'm going to do is walk through the 3 years of Instagram. I'll spend most of the time on the last year, because I think that's where we've had to sort of make some interesting trade-offs and where the simplest thing stopped working, which I think is that's the next point where you're like, okay, we did the simplest thing and now it breaks, and what do you do then? But walk through years 1 and 2 first. Year 1 is all about scaling up. So as if it was as easy as this. So we launched, all of a sudden it's, people are actually using the app. I had 0 infrastructure experience at all. We had 2 total engineers, neither of us really. One of us, or the other one was a former Cold Fusion developer, so it wasn't exactly like we were working on cutting edge technology. And our attitude at this point was scale just enough to get back to working on the app. Because what was going to differentiate us in that first year, it was our ability to keep moving on product and iterate on user feedback and stay ahead of everybody else who was trying to encroach on our space. It wasn't like, how well did you scale Postgres? Of course, if we failed at that, that would be very apparent. But in terms of user-facing things that were absolutely critical is time spent on the app. With 2 total engineers, every hour spent on infra is an hour not spent on product. So every weekend that we made it through, our peaks have always been the weekend, was a huge accomplishment. So on Friday, we would see like, all right, what's going to break this weekend? How can we do it? I called it like just-in-time scaling, and it's a pretty exhausting thing because it's a weekend one after the other, and you can do the 52 in a row, and you've got a year, but you're going to be completely burned out by the end. Major challenges then. First one, as I think is the case for a lot of startups, is scaling up your data store and your database. This was back in the day before Amazon had any kind of provisioned I/O that you could buy for their elastic block storage. So your option was raid a bunch of them together and hope for the best. Of course, if one of them was in a bad mood, there's your whole raid that will suffer. So at the time, you could get 400 IOPS if you were really lucky, which is really pitiful if you think about it. They just launched an instance at reInvent this week that has 350,000 IOPS. So they've come a long way. But in order to scale up our data store, again, we did the simplest thing first. So things are on fire, we're looking around, we don't really have time to work on the infrastructure, so we went for vertical partitioning. We use Django as our application framework. At this point, it's a pretty modified, hacked up version of Django as you get 3 years in, but the guts are still the same. And one feature they have that's actually served us really well back in 2010 was database router. So at the middleware level, you can say, route all the reads for this particular model to this database, all the writes to this database. You can write the reads to one and the writes to another one if you have a read slave, for example. The really beautiful thing here was we took these 4 partitions. We had media, which is photos. We called them media at the time. We had a little bit of like foresight, like maybe we'll do video one day. And then we had likes and comments. Likes was by far our most rapidly scaling one. And then we had the everything else database. Fun fact, there still is the everything else database. There's some stuff that you never end up sharding years in, right? And we were using Postgres. We're still using Postgres. And they have in 9.0, which is what we were using, a pretty good replication feature to bootstrap the new nodes. So we had our master database. Now we had our master database that was going to become the likes database. Cut over, promoted as a master. Spot us sometime, like even intellectually as you're doing that, you're like, this is not a permanent solution, but it was enough again. All right, that got us through like 3 or 4 months of extra time of like, all right, let's go back to working. Let's add tagging to the app. Let's add user mentions. Let's improve notifications, et cetera. And the really nice thing was, again, almost no application logic changes. I think if you were starting this Instagram today, I think you could probably skip this step because the provision IOPS and the SSD instances will get you much further. And really what the bottleneck we hit was both write and read performance on I/O, and I think you would get to defer that for a lot further, which is nice. For our less durable, more sort of in-memory feeds, inboxes type of things, we were using Redis from day one, which was kind of an interesting move in 2010. Like I think at this point at Redis is people trust it. Amazon even has it as like an offering for their Elasticache, but it was like, I think we'd seen and heard that it was an interesting technology. I think it was at like 1.2, but it was stable enough that we felt okay rolling out. With Redis, as if you're familiar with it, it's purely RAM bound. So there's persistence for durability, but there's no swapping out to disk. The author tried adding this feature for a while, and he's like, I give up. Like, it's never going to be as good as a database. We should just focus on what we're good at, which is to be in memory store, which I think is actually a good decision. And the way it does persistence is at a configurable interval, it will fork, and it will use copy on write to persist the data to disk. And with Redis, unlike with Postgres where we just plugged into the database router, we had to really start thinking about, all right, like there's some vertical partitioning by data type, but since the keys were just like in a bag and we didn't have the prescience that companies at Pinterest had around, for example, pre-sharding or putting them into separate sub-databases inside Redis, it was pretty messy. So there was no easy migration story. It was mostly around double writing from scratch. The good news is Redis, we're usually dealing with like a hot, like 2 weeks of information even back then, like your feed, your inbox, those types of things, and we weren't really doing more persistence, like we're going to need data from a year ago in Redis here. We also found that like the kind of equivalent approach to how we resharded Postgres, or how we vertically partitioned Postgres, was replicate and delete the data that's no longer active on that node. It doesn't really work with Redis because once you delete even like, talking tens of gigs of data, it's going to leave it pretty fragmented, and you haven't really reclaimed that data. So you end up doing like, if you ever break an egg and you try to like get the egg white out but not the yolk, that's what it feels like with Redis. You're like moving it from one side to the other. And finally, we had memcache scaling, which was actually the easiest, I think, for us. We just used consistent hashing in Katama, which already in 2010 was like the best known practice around not having one end of your node, of your keys drop out if you add one node. One gotcha back then that hit us was mining that hash function. So you're like, oh, it's Katama, it's easy. Just like plug in this other memcache library that does Katama. But like, there's some very subtle gotchas around like, well, do you take the host name and the IP and you concatenate them with an underscore, with a dash, and it's usually hidden pretty down deep in the C library or whatever that you're using for memcache. And like, I've now been traumatized enough that whenever we roll out any kind of caching change, we just run a battery of like, is it generating the exact same type of mapping for this particular input? So one minor gotcha. One question that we get often is why weren't you using Redis for your key value caching? I mean, you had Redis, like wouldn't it have been easier to scale one technology? Wouldn't that be the simplest thing? And the answer about why not is the best and worst part about memcache, which is the Slab allocator. So the fact that memcache, if you tell it take 30 gigs of RAM and no more than 30 gigs of RAM, it is not going to take any more than 30 gigs of RAM with very, very, very few exceptions, right? It takes that space, it carves it up into slabs, and then within the slabs, it's doing its own allocation. Redis can use a bunch of different memory allocators, but none of them are like this. The advantage is that you don't get the sort of like slab calcification you get with memcache, where if you really change your data types, your host. You get a more subtle problem though, which is 30 gigs end up being a recommendation, and then a year later or even a month later, you're like, oops, 30.1. You're like, that doesn't sound good, and then it's 30.2, and it meant that we had to like massively under provision or cap our Redises at a much smaller amount than the actual RAM capacity of it, which when you're early and you're broke, it's not great, right? It's like now we're paying even more money for these EC2 instances. So ending the year here, I was doing most of the infra work, and it went from about 10% of my time to about 70% of my time. So luckily, we had brought on like one other engineer so they could work on the app in the meantime. But focusing on the client was becoming increasingly difficult. And we had some things in place, like we had unit testing from day one and functional testing, which made it so we weren't rolling out things that were on fire all the time. But I could tell that there were a bunch of like ticking time bombs that were about to hit us in year two. So this is when we started scaling out, because we rapidly realized, well, that vertical partitioning strategy was great for 3 or 4 months. It was the simplest thing, and now we still only had 400 IOPS max, and we have a ton of likes happening. So here's where we tackled the database scale out and the Redis scale out. There we are, pre-SSDs out of I/O, and this actually was we're about to make the mistake. You can cue the scary music of our scaling sort of story. And that was thinking, well, maybe we should do our primary data store as a NoSQL solution. So what we did is we called our friends and we're like, guys, like, what are you guys doing? Like, what technologies have you been using? I had a lot of good friends at Couch IO was doing CouchDB, and they were like, okay, you might want to use Couch, but it's operationally complex. I had worked at Meebo that had a huge CouchDB deployment, and after seeing that, I'm like, I'm not sure I want to put this in production with one infra person. Other friends were like, well, like we tried Cassandra, and like it's pretty complicated to keep in maintenance. We also called some strangers. Like we got friends of a friends to introduce us to. We called Dig, and we're like, hey, what did you guys do with Cassandra? They're like, you can get to the point where it works, but it's not going to be a passive thing. It's going to become somebody's full-time job or multiple people's full-time jobs. And our theory here was that partitioning and rebalancing were the hard parts, and we should let the database take care of it. Like when I thought about what we were going to be as a company, it was not a sharding company. It was a social company for people sharing their moments, right? It's like, what do we actually want to be good at? So after a lot of process of elimination, we're like, all right, we're going to try MongoDB, which was 1.2 at the time. And we did the standard migration practice, which you start double writing and start doing shadow reads to see what kind of performance you can get, read from both, compare, measure your drift in terms of the consistency. And we spent a lot of time stressing about the primary key of the database. So we're like, okay, they have these BSON object IDs, and can we compact? And we actually got very good at bit manipulation for IDs, and it's usually a bad sign when you've spent 2 weeks mostly just stressing about how to efficiently pack all of your data in your primary keys, and you get into these denormalized systems common problems where all your field names are now called you, or the emoji for smile or something, just because you're trying to compress the space as much as possible. But we felt okay enough to put it in production as a second read system and double writing to it. We put it in production, turned on the knob to start reading from it, and we started seeing all sorts of weird stuff. So there was a moment where we had a replica, and I was like, wow, it must do this really cool compaction step when it creates a replica, because this one is 30% the size of the other one. And then I was like, oh, wait. And then you look at the row count, and that was not true. And we also hit all sorts of segfaults, and it was just, again, I've been tracking. I can't remember my Jira password, so I can't unsubscribe from these bugs. So I hear about updates from them. Most of them seem to have been fixed by now. The feeling that I had was we could have made this work. These weren't insurmountable technical challenges. We could pretty much figure out what was going on. We could tell that, for example, when you rebalanced a node, the thing that was killing it was all the I/O on deleting the data on the old node, and those deletes weren't yielding as often to the application, stuff like that. But again, it would have been somebody's full-time job, and we had 3 people. So imagine taking your entire infra team and saying, you are now working on MongoDB for the next couple of months. So we still have this train, and there's a rapidly approaching cliff that we're about to fly off of because we're almost out of I/O. You could see the graphs in Munin, and they would go like this in terms of I/O, and then things would really rapidly cliff because at some point you're doing so much contention for the stuff in memory that your working set isn't fitting in, and you're paging more and more and more to disk. So we're like, all right, can we do the sharding in Postgres? We already have Postgres. We've been using it for a year and a half now. We trust it. Sharding a database is how Facebook is scaled. Other places we called again. This is calling a bunch of friends. How did you scale? We were really fortunate to have Adam D'Angelo, who's one of the original CTOs here at Facebook, as an investor. So we could call and be like, Adam, how did you guys do this, and what would you do differently? So there's a bit of infra foreshadowing that we ended up clicking really well as a company inside Facebook in terms of taking a similar approach. So this is an approach that has been discussed before, but I'll go over it pretty briefly. It's just logical partitioning done at application level. So none of these fancy MongoS routers or magic rebalances. We skipped all those abstractions and proxies and just pre-split into n logical partitions. In our case, it was 5,000, which I'm going to blame on my lack of sleep at the time, because next time I'm going to pick a power of 2, because 5,000, if you keep splitting your partitions, you will actually never hit. So you can probably get a sense of our state of mind back then. So what we use for this are this somewhat known Postgres feature called schemas, which I don't know why they named it this, because it's actually really confusing, given that schemas is a pretty overloaded term when you're talking about databases. Conceptually, think about it like this. We have a database that has schemas inside them. The schemas contain tables. Table contains columns. So I think the equivalent would be like a MySQL database. The advantage is you can have one connection to the database, and that connection can talk to all the different schemas. The trick why that is important is connections in Postgres are actually pretty expensive, so you don't want to have connections to a bunch of different ones. And then within a machine or an instance, you have multiple shards. They have all the same table name. It's really nice in your application code to just be able to connect one, select a schema using the use or using keyword, and then you can have the same table names. And then for resharding, and it looks like Keynote has done amazing things to my font size here, but you can take machine A, which is your original one, use streaming replication to create machine A prime, which will have the exact same schemas, and then drop half of them on the new machine, half of them on the old machine, and your application is now talking, writing and reading from the right applications. The really nice thing here versus Mongo, where like doing that delete after the rebalance kind of left you with a Swiss cheese of a data file that was really fragmented, is each schema is contiguous on disk. So dropping a schema means like that whole file is gone. It's like you're set. There's no fragmentation happening. This is still how we scale Postgres today. Like it's lasted us years. It's a strategy we feel really good about. We've obviously placed a lot more automation around this process since then, but it's still like a tested, tried and true technique that worked. Even for 9.2, the one gotcha is that Postgres' replication is all binary, so it can't replicate across versions very easily. So we use a tool called bucardo, which is a trigger-based replication, only as sort of a migration moment between the two of them. Like handling the trigger-based replication for a longer term would probably have been more operationally complex, but it was like a point in time when we just like switched over to 9.2 and then we were done with it. The remaining challenge, and where we also like tried to do the simplest thing first, was ID generation for our sharded database. All of a sudden, your primary key isn't just a sequence that you can auto-increment. We had a few requirements in our head. The very first one, I think the most important one, was no extra moving parts. So for us, like, again, doing the simplest thing first, with 3 engineers, the last thing you want is to like have yet another system to administer that's gonna have its own bugs and problems, its own uptime, its own problems. We wanted to keep it to 64 bits, and that was application constraint. And we wanted them to be time-ordered and contain the primary key. So there's a lot of options out there, like Snowflake is something that Twitter open sourced that does ID generation on a per node basis, and you can talk to it, I think, using Thrift. There's been a couple of other solutions this way. What we decided to do is say, all right, we already have our database. Like our mindset has shifted from like, let's try these NoSQL things, so, like what else can we do with Postgres? I think sometimes people take it too far in the other direction and end up writing like, we can do our like queues in Postgres, and we can do like our whole logic in Postgres. Like we were like, all right, can we at least do IDs? They seem like they belong there. And we wrote a PG pSQL function that's definitely a write once, read many times language. Like I never want to edit that file ever again. But we basically were able to stuff all the information we needed into 64 bits. This approach was similar to how Snowflake does things, but we have the Instagram epoch, which is in 2010, so we can fit 41 years of IDs. I hope we're not using the same partitioning scheme in 41 years, but if we are, we'll have a problem. A logical shard ID, which actually fits 8,192, not 5,000, so we can actually do some jiggering later if we want, and then an auto-incrementing sequence number that's per database, and for that we just use the built-in Postgres sequence ID. So what's nice about this is we can generate 1,024 IDs per shard, per table, per millisecond. Our write rate is nowhere near that even now. And we really learned this lesson of having a new database is a real full-time commitment that we really could not afford to have taken at that small point, and that was the sort of fork point back then. And it's nice to be thrifty with your existing technology and minimize your moving parts, and that was how we've approached that thing. So ending year 2, the database was by far our biggest scalability challenge. And then Redis scaled in a similar way. We were still using our vertical partitioning, double writing. But we were able to launch an Android app. So we launched that in 2012 in April. And basically doubled all of our infra for that launch, which was nice that at this point, most of it was horizontally scalable. Like we could add twice the Postgres capacity for almost all of our tables, which was great because what happened in the next 6 months is that we doubled our active users. So we basically had to double one more time. And we were fortunate / we had been pressed to make that change about just in time to the point where we could add database capacity pretty much in time. And we were finally slowly building up our team. I think we ended the year with 4 people, 3 of whom were more focused on infrastructure. So year 3, which takes us to the present, the 2 main themes have been stabilizing and replacing some of these technologies with things that are maybe more complex technically but less complex operationally. Again, there's that trade-off. And then also integrating here at Facebook. We came down here in September of 2013, so 2012. We've been here over a year. The first system that we rolled out we called knobs, which I'm told is a dirty word in England, so we can open source this in github.uk. So basically the intuition here is we had to scale cutovers, ramp-ups, and development. We had a lot of like, all right, we have this feature, we want to roll it out to 5%. All right, now we want to roll it out to 10%. Whoops, down to 0%. And if you look at our Git log, back then it was like 5%, 10%, revert 5%. You know, it's like a pretty unscalable solution. And these dynamic ramp-ups and configs became ever increasing in need. For example, doing a database cutover. When we were doing bucardo, we wanted to switch our nodes over. And we required a deploy at this point. And we started looking at more complicated solutions. Like you can do this in Zookeeper. You can build scaffolding above Zookeeper to do this. There are other config management systems. But again, like we're still not huge. Like to this day, we're maybe 10 to 15 people who focus on our infra full time. So we ended up making a Python knob system that's the simplest thing we could think of. So you use only integers. So you can only write ints to it. You can't write strings. You can't write lists. You can't write anything else. It's all stored in Redis, which we already know and have a bunch of Redis deployed, and we were able to use an existing Redis cluster for this. It's refreshed every 30 seconds, so you have a reasonable amount of freshness. This isn't for stuff that needs to go out to every database or every app server at the same time exactly, but it's good enough for what we needed. And we built this cached Redis set. So it acts just like a Python set, has the same semantics, but every 30 seconds or 30 to 60 seconds, it's refreshing itself from its backing store. The API is dead simple. Like, the types of calls you can make are getting a feature name and passing a default. And then when you want to do a ramp up, we have more of like a volume-based one where you go from 0 to n, where you can define the n as well. And like I'm sure you've experienced in your own companies, like once you build a piece of infrastructure that's simple but also really useful, people just start using it for all sorts of things that you didn't even intend it to. So feature kill switches are now implemented using knobs. We do dynamic page sizing sometimes on the weekends when the load is really hot and we basically have to shed a little bit load. We can lower the number of items returned. And the original feature was incremental feature rollouts. The other nice thing is when you build something that's useful and simple is people end up building like additions to it. So we have a web UI, which is like, this is a small portion of the web UI. So that like you can actually edit this on the web. Like if you're on your mobile phone over the weekend and you want to make a small change and turn something off, obviously over the VPN. But it's been really useful to see that. And this is a product of a Facebook boot camper. So somebody who's like not even on our team, but was, hey, like I have 6 weeks, I'm choosing a team, your team seems interesting, like maybe I'll build this web UI for you guys as a project. It's been really useful. The other hidden benefit that I couldn't have predicted when we developed knobs is as more teams around Facebook are contributing to our code base, having them tied to our release process, we'll ship code 10 to 12 times a day or more, depending on when it's available and when it gets rolled out. So we get continuously integrated and rolled out pretty often. It's been really nice to decouple the deploy of the code from the enabling of the code. So we like might deploy an engineer on the spam fighting team's code in the morning, but it's off behind a knob, and then like later in the day, once they're ready to go, they'll sit down and turn it on. So that's a nice side benefit. The other theme of this year has been taking some of the technology that, like I mentioned, was simple in implementation, but became harder operationally. So a really good example are our inboxes. At this point, our databases are stable. Like I feel great about our database scaling story. The next big step is like working with the Facebook database team to like see how we can automate things so that it's less of a hands-on thing. But now our other stores are acting up. So take our inbox. So if you use the app, over on this fourth tab over here, you have your inbox. And this is activity on your photo. So this person liked your photo. They commented on it. Your Facebook friend, John, just joined Instagram. Here's his username, things like this. And for the longest time, this system was in Redis. This was in Redis from basically day one, like when we shipped code in 2010. And sharded by user ID as soon as we started sharding out our Redis clusters. And this Redis API was a good fit for this. If you wanted to add an activity, you would push, which means push onto this list. And we would serialize a thrift object and then stuff it into Redis under that user key. So you had one long list. And if it was time to trim, you would say, like, trim this user key to the 99th element. And since it was just sort of appending, and then we'd probabilistically trim it about 10% of the time. We had about 32 nodes that were 68 gigs each. And we were starting to get to the point where the in-memory Redis data was starting to approach this, and at this point it was like, okay, we're gonna have to like split it again, double write, and it was gonna be a complicated project. The other big problem was we were in a master-slave setup, so every failover was like a 4 a.m. page for some poor unsuspecting on-call. And again, we had like 5 people, so on-call, it was basically like every other week for most people. So really we're trying to avoid this like getting paged in the middle of the night and waking up. And the in-memory requirement was really starting to bite us in year 3 of the company. In year 1, most of the people are signing up and using the app. By year 3, you have people who came, they used it, maybe they don't like it that much anymore, they left, maybe they have a different username now. So we were paying for every churned or inactive user to be kept in memory. Even with expiration, because of the fragmentation issues I mentioned earlier, it wasn't a reliable, like, oh yeah, just expire people after 30 days and they'll be fine. Because deleting keys does not reclaim them. And finally, as we got close to the memory limit, Redis's fork and copy on write background save feature was becoming our real-life version of the movie Speed with Sandra Bullock and Keanu Reeves, which is you have a race between the background saving process, which is increasingly taking up more memory because of copy on write, and your maximum data, and it's really scary. And like I think I've lost years of my life to watching Redis BG save and doing free-m in a watch and hoping that it doesn't overshoot it. Whenever we wanted to restart it was somebody's full-time job for 2 days. Like set up the double write, make sure it's working properly, do a bunch of code changes. It just sucked. So this is a case where the simple thing first got us pretty far, but it was clearly just breaking, right? Like at this point, it was the simplest to set up and administer for a while, but we were way past that point. So it was time to reevaluate. And we moved the inbox to Cassandra. And the funny part about Cassandra is whenever we mentioned we're using it inside Facebook, like, we like got rid of it and like we don't really use it anymore, right? And we're like, yeah, like it's definitely evolved a ton in the open source community. The write read rate for this particular system matches Cassandra relatively well. It's not like a super read intensive system, it's about even. But I would say the prereq to us deploying it internally is having Rick Branson work with us because he's ex-data stacks, he knows Cassandra, he's a committer. So I'm still not at the point where I would like recommend just rolling out Cassandra without somebody who has like deep expertise in it. It wasn't a full-time job for him inside Instagram, but it was, for a while, it was a lot of technology or consideration of how to use it. So we use user ID as the row, and we have a bunch of columns that are sorted by time UID, so like they're unique and they are at the insert time of the activity, and the activity is still these thrift serialized objects. It was the easiest thing to migrate to, just serialize the same thing, but put them in Cassandra instead. For trims, instead of the symbol LTrim, what you can do is insert a row tombstone after that stale time. The nice thing there is that it'll know from the metadata of the row to stop reading at that point and say like, all right, I'm just gonna return the data that's at this point or newer. And because it's temporal data and it was a transition that we could make, over a couple of weeks of double writing, we felt comfortable like, all right, we have most people's inboxes that are gonna be valid anyway, because if you have any amount of activity after a couple of weeks, all of your data is new. We're pretty happy with the performance of it. It turns out most of the latency in almost any of these systems inside AWS just comes from the network inside AWS not being particularly awesome. If you measure it on the node itself, we're talking like 3 to 4 milliseconds, and then there's obviously the like, well, they get queued up at the driver, and then it gets sent over the wire on EC2, and this is from trop to peak. So in the middle of the night when it's kind of quiet to the peak, you see our P90 times like tick up a bit, but still well within what we were seeing with Redis anyway. And the Cassandra cluster is 35% of the size of the Redis one, which is really nice. It's like fewer machines to administer, and because it can page to disk, like we don't have this like in-memory requirement that was really biting us before. The one challenge that I'll highlight, because I think it's kind of an interesting technical thing that we solved, was handling deletes in a way that was actually in fitting with the Cassandra model. So this is the moment where you like have to shift your thinking as an infra team. It turns out 10% of actions are undos. Like maybe you posted a comment, you don't want it, you delete it, you liked something, you unliked it. There's a fair amount of undos that happen. The Redis way is really easy. You just LREM, which is remove this from a list. It's an ON operation, but it's not. It's a list of 99 items, right? And the thrift object gets removed. The trick here is the thrift object has to match the one you inserted, so there's some little tricks around that, but pretty easy. And this is fine for a system that emphasizes consistency over availability, right? Like, you know that when you do that LREM, the next time you read from Redis, it's going to be fine. It's going to have the exact same data, and we only ever read from the master on Redis. It's not so hot for a system that emphasizes availability over consistency like Cassandra, where you're going to have this eventual consistency issue. So say you're here and you do a delete right here. I want to delete this like. So you do a get and delete. Problem here, of course, is the state of the row may have changed between these two operations, and where you're reading from may have changed as well. So to put it in more concrete terms, and I'll stand back so you can see it. Imagine there is a insert of B, like data point B, and you have 3 replicas, and let's say the first 2 succeed and the third one fails. So read repair will eventually get around to like putting it on this third replica, but you don't know when, and you can't really be guaranteed unless you want to do like a blocking or a like consistent read every time. You don't really know that B has been written to all of your replicas, right? If you then go to undo the like, you're going to do a read then write, and when you do the read, it's going to say, well, I don't even have a B, so there's nothing to delete, so maybe your code's like, well, I'll catch that exception, right? Like, you failed to delete this thing on the other replicas. So the technique that Rick cooked up is anti-column. So this is a technique that's been used in the Cassandra community that we ended up adopting, and the idea here is instead of trying to modify the row, what you create is an anti-column. So something that sorts at the very, very beginning of all your data. So we have sort of a marker at the beginning, which is a 0 or a 1. And the anti-column actually represents the value of the data as an MD5 hash. So basically, everything that gets deleted gets placed in an anti-column, representing, like, get rid of this data once you see it. We always read both of them when we pull it out. So we'll pull out your latest activity and the anti-columns that match since the tombstone that would have marked the row, like, only see data newer than this activity, and then we can dedupe and say, all right, we see an anti-column for these pieces of data, let's pull them out. If we see an anti-column and we don't see the piece of data, then that's like an eventual consistency issue. We can just ignore the anti-column. The good news here is, let's replay that scenario where we inserted B and the replica, our replica number 3 never got that right yet. When you go undo it, we're actually inserting C, it gets replicated. Even if this fails, like, we're actually going to converge on a source of truth that is actually reasonable. Let me read them both. So this is a good example of like shifting our mentality from, this is not like a rocket science solution. It's basically like the reality within an availability-based systems. You want to do things that are relatively immutable and think about things in terms of mutations that you can capture versus reads and writes. I'll highlight that our main feed and our timeline is still in Redis, which is still an operational problem, as the infra team back there can attest. But we have a really, really high insert rate, and we haven't really found a good system that replaces it. But this is definitely like one of our top 2014 projects, is working with Facebook to see how they've solved this across their infra and see like, well, what technologies can we adopt that solves the same problem. On that note, on the Facebook side, the real question we keep asking ourselves here is like, where can we skip forward a few years at our own pace, which is kind of an interesting distinction. Like the pressure has not been like, all right, like day one, you guys are migrating like entirely off of your stack to our stack and like double writing being done. Like what I've actually really appreciated here has been like, all right, like where do you want to skip forward a couple of years? Like what work can we save you? And then how do we make your team more effective? So the first huge win was spam fighting. So this is a great case of the simplest thing first does not really work very, very long. So this is like our, people would be like, follow me on Instagram, and they would spam comments, and you quickly play this like losing regular expression war with the spammers, right? This is like a completely unsustainable way to fight spam. The simple thing does not last. So Facebook has a site integrity team. It's an amazing team. We were able to like basically plug it in because it's basically built around generic features and machine learning, and then custom actions taken on a particular action. And you should have seen the spam amount on Instagram from then to now is like a dramatic drop. We had Jamie Oliver, who's this like celebrity chef, email. He says like, "What did you do with the spam? It's all gone." Which has been good validation of our community. Also plugging into things like Hadoop, Hive, and Presto, like not having to run our own Hadoop cluster. I used to run Hadoop clusters for a living. It sucks, right? Like it's like, oh, this name node's down. Okay, like that's like another hour of recovering stuff. Or oh, the job's 99% done. It's because that thing is slow. It's a full-time team's job, much less like one person on your sub-team. So being able to plug into that, getting used tools that like are internal before they're open source, like Presto, has also been great. There's also the like more broad question of like, you can sit there and say like, well, I wonder how they solve this one. The Redis feed is a good example. Like Facebook has feeds too. Like that's definitely a conversation we're having with the feed team as well. And it's been a two-way exchange. Like there was a lot of curiosity, like where does Redis fit in and what is it good at? And I think we've had our fair share of Redis war stories and successes and failures. So it's been good to exchange that as well. And we have like what I call a 2010 vintage infra, which is interesting to poke around for a company that has an older vintage that is more established now. I'd say the number one impact has been on recruiting. So our tiny team is slightly less tiny, and we have like just over 10 people now on our backend team, which means we can take like slightly different approaches. So just wrapping up, what I kept emphasizing, but I really hope you take away from our philosophy to this and possibly apply it to yours, is really doing the simplest thing first. In a tiny team, it means that you're not constantly wondering like how this failure mode could have occurred if you try to keep things and things understandable. And I'll posit the flip side of it is the time to reevaluate is when the simple solutions get more complex operationally, which is what happened, for example, with our inbox in Redis. Feel free to reach out at any point on mikeyk@instagram.com if you have any questions or want to compare stuff. One of my like personal missions is getting people working on this stuff together more often. I had this great chat with the Pinterest guys last week, and I was like, guys, like we've solved basically almost exactly the same challenges in very similar ways, and we've never really talked to each other. So that's one of my goals. So anyway, I'd love to take any of your questions, and thanks so much for coming.
Hi. Just like to know how the anti-columns work. You mentioned like use anti-columns to detect like whether the replica has been actually passed or not. So is the anti-column to replicate it to all other shards?
It will be, yes. So it's just another write in Cassandra, so it'll be replicated to all the other shards as well. So the system, you still have the state where the anti-column has not reached a particular replica,
Yeah.
so
Yeah.
you aren't guaranteed that it will be deleted like perfectly, but at least the system converges on a state that is actually real versus the read then write case where you've created a moment that will basically never converge onto the actual reality. But yeah, there is still that window of like,
Okay,
well, if
yeah.
that write fails, yeah.
Okay, thank you.
Hi, I'm Abi from Pinterest.
Hello.
Talk. So you said Django, and so I'm assuming you use Python. And so was there any like scaling issues with application servers written in Python?
I would say the scalability issues there. There were some that were Python performance driven. Like we used to do our Katama hash ring in Python, and doing the bisection of the hash ring in Python ends up being pretty slow. So we wrote a C module and just like used, there's like 4 different ways of like hooking into C code from Python. I forget which one we used for that one, but we basically have a C library for that. I'd say the other problem that we had pretty consistently that we've kind of like gradually evolved towards is the question of like how you actually run Python, like what your container is. So we used Unicorn for a while. Unicorn was pretty good. It had some issues when you had a lot of like simultaneous process running. It had some issues with code reloading. We now use this thing called uWSGI or muWSGI, which has served us pretty well. So it's less about Python and it's more like these sort of realities of running Python in production. But we're not memory bound, so like the fact that Python might not be the most efficient memory bound thing or memory thing in the world is it. We're purely CPU bound, and the more we instrument, it's talking to backend services and also string manipulation. So that would be one area where like finding out how to move that to a lower level language would help.
You said you looked at Cassandra. Did you look at any other databases also other than Cassandra?
So back when we were wondering whether to shard.
From Redis,
so, yeah. So we looked at Couch, we looked at Mongo, we looked at Cassandra. We looked at HBase, but it really didn't seem like a good fit for like your main application store for everything. We wondered whether switching to MySQL and like being really, really similar to Facebook would be the way to go, but it seemed like then we'd introduce a new database, not really for any reason, given that we'd be doing the same amount of sharding. I looked a lot at some off-the-shelf like sharding things, like there's a couple out for Postgres that Skype has written. Skype writes, I think, very good software that's very hard to understand if you're not like at Skype. So like, I think we would have gotten it to work, but I was like, I don't know how to do it. I don't really want to be like the other user of this technology, and we weren't really sure who else was using it. It is frustrating to me that like doing logical partitioning of databases still feels like an unsolved or resolved problem by everybody in 2013. So maybe something will come out for Postgres or is under development that I'm not aware of that will help with that. But those were kind of like the spectrum of things that we looked at. Yeah, those were the big ones.
I was actually just wondering about the, you talked a little bit of the hash ring in Katama. I was wondering what hash you guys selected or how you went about that. Like I've seen in the past a lot of interesting behavior about variance between shard size when you're using Katama, especially with like an MD5 hash. So I was just wondering how you guys were both resistant to any avalanche behavior and also got good distribution among your hashing.
It's like the infra team knows. Rick, do you know what we use for our hash? What do we use? I think it's MD5. We use whatever the built-in one is. So we don't have our own custom hash function. Like we don't choose a custom hash function. We see hotspots more of the Justin Bieber variety than the key space distribution variety. It's definitely not even. Like you can see on the ganglia graphs that like there are definitely it's more of a wave than it is something totally flat. But again, like it's really the who liked Justin Bieber's latest photo. That's the really painful one to answer. The Bieber problem. I wonder if he knows how much heartache he's caused for every scaling social network in the Valley.
All right, let's thank the speaker. That's
Cool.
the time we have for questions.